She wrote the book. Her maiden name is Sullivan.
They just had done it right the first time, and I wouldn't have had to. What can I say? All right, so we are, all chapter 5 is probability. It seems like probability is fairly simple as we go through each individual piece, but when you have to add the pieces together, it gets more complicated. So the way I kind of do it is I'm going to go through chapter 5, the probability chapter, fairly quickly, but then when we get to the end of chapter 5, we are going to spend a lot of time just putting all the things together. So we'll go through all the individual lessons, and then we're going to have like a week of just using it all together, so we can kind of figure out when we do each individual thing. So some vocab, if I'm just asking probability, that is the likelihood of an event occurring. What is the probability of this happening? What is the smallest probability you can get?
0.
0. You can't have a negative chance.
Didn't realize that was.
What's the biggest probability we could get?
100.
100%. Okay. Second thing, law of large numbers. As the number of trials increase, the closer the probability gets to the expected probability. Okay, that seems a little confusing, but let's think about it. If you flip a coin, what is the probability that you will flip a heads?
50%.
50%. Would you agree with that?
Close.
Okay. Now, does that mean if I flip it 10 times that I will get 5 heads?
No.
No. It's 50%, but we know it doesn't always work out exactly like that. But if I flipped it 500 times, do you think it would be more or closer to 50%?
Yeah.
Yeah, and then if I flipped 5,000 times, would it get even closer? Yes, that's the law of large numbers. If you only do it a couple times, it may not be the probability we expect. But if we do it the same thing over and over and over again, it should approach the real value. And I think all these definitions are just on that first slide. So sample space, sometimes that's just called S. That's just a list of all the possible outcomes. If it were flipping a coin, what would my sample space be? Heads and tails. If I said I'm going to flip it 2 times, I could have heads, heads. I could have heads, tails. I could have tails, tails, or I could have tails, heads. So a sample space is every outcome that you could occur. An event is the collection. So it might be that I flip my coin 3 times and I get heads, heads, tails. That's an event. I had this occur when I flipped my coin. So let's just jump in with a problem. So consider the probability experiment of having 2 children. Identify the outcome. So if we are talking about 2 children, I guess I wasn't clear enough. I'm referring to gender when I say the outcomes here. So if we're talking about the possibilities for gender, and we have 2 children, what are the possibilities?
Boy and girl.
We have boy, girl, but we have
4 combinations.
Yeah.
Which is
so the individual outcome is just boy or girl. But if I say the sample space, that's listing every possible combination. So it could be that I have 2 boys. Or it could be that I have a boy and then a girl. Would it be different to have a girl and then a boy?
Yeah.
Yeah, if your oldest child is a girl and your youngest is a boy. Or the last outcome is girl, girl. Okay, so the outcome is just the different possibilities, boy or girl. The sample space is where we list everything. If I wanted 3 children, then my sample space would have been like boy, 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 girl, and so forth, listing those combinations. Define the event having 1 boy. So which of these are having 1 boy?
Boy and girl.
Yep, boy, girl, or girl, boy. Those are the 2 ways you could have 1 boy. Any So a lot of times with probability, we are going to talk about probability models. With that, we have a couple rules to keep in mind. So probability, we said, has to be between 0% and 100%. In terms of decimal form, that would be between 0 and 1. So probability has to be a number between 0 and 1. If it's not, we messed up. And if I'm listing all the probabilities that could occur, they have to add up to 1. So the sum of all the probabilities must equal 1. So a probability model is when we list each outcome along with its probability. Here's what can occur, here's the chance that occurs. If an event is impossible, it cannot happen, what would the probability be?
0.
If it is certain, we know it will happen, what's the probability?
1.
And then
Just 1.
the last, the definition of unusual. So unusual is something that can happen, but usually doesn't. And the guideline is it's typically anything less than 5%. And we will use that term a lot. So unusual is anything with a probability that is less than 5%. It can happen, but it probably won't. Probability of every single student in the district showing up to school tomorrow. Can it happen? Yes. Is it likely to happen?
Absolutely
No. Does not happen very often. So less than a 5% chance is unusual.
I think we should celebrate that.
Yeah, that would be a big deal. Okay, so let's create a probability model. Suppose we have a bag of 100 M&Ms with 12 brown, 15 yellow, 12 red, 23 orange, 23 blue, and 15 green. Create a probability model. Okay, all this is essentially a table where we list each outcome and its probability. Okay, so my outcomes are my colors and our probability. My colors, we can list them in any order, so brown,
We got a yellow.
that's Clara's favorite color.
I just didn't even see it.
Alright. And then we list the probability. So if I'm eating my M&Ms and I pick one out of the bowl, what is the probability that the one I select is brown?
12%.
Okay, so typically we list it in decimal format.
Oh.
And we get that just by doing 12, because there are 12 browns, out of 100, because there are 100 M&Ms in my bowl. So the probability of a brown is 0.12. About a 12% chance that I select a brown. So a yellow, there's 15 out of the 100 in the bowl, so the probability of a yellow,
0.15.
a red, 12 out of 100, 23 orange, so 23 out of 100, 23 blue, and 15 green. If this is a true probability model, every probability is between 0 and 1. So quick check to make sure we didn't make a mistake. Is that true? Is everything between 0 and 1? And if it's a true probability model, what does it have to add to?
1.
Okay, check yourself. If you add those numbers, does it add to 1? All right, so we're good. That's a couple questions on your homework. Gives you a chart pre-made and just asks, is it a probability model? That's what you're looking at. Make sure each individual number is between 0 and 1 and they all add up to 1. 100% chance. All right. So there's technically different kinds of probability. There's, so one of them, the empirical approach, is what we just did. So probability is equal to the number of times it's observed divided by the number of repetitions. We have 100 M&Ms, we knew 12 of them were brown. That's different than if I said I took a bowl of M&Ms and I selected 5 out of it and 3 of them were brown. Okay, this was based off what was actually in my bowl. So just another example of calculating that. So it's just the number of times we got the outcome we wanted divided by the number of trials. Part over the whole, that's how we find a probability. So an insurance agent insures 182 teenage drivers. Last year, 24 of the teenagers had to file a claim on their auto policy. Based on this, what's the probability they file a claim? So it's just part over the whole. The number of trials is the denominator. At the top is how many of them were the outcome we wanted. So we want to know how many filed a claim. So how many did file a claim on this?
Like 182 or 20.
24 out of how many total?
182.
Okay, so if we divide, doesn't work out nicely, so let's do 4 decimal places. 0.1319. So that's just based off what we've seen happen. Out of my 182 customers, 24 of them filed a claim. So this is what I expect.
So if it asks for probability, you want it in decimal. So if it asks for percent, you want it in like an actual
Yeah.
10 to 100.
Pass the pigs.
Usually we'll take either. I
Okay.
don't really care. Okay. Have you guys ever played Pass the Pigs? Oh, we need to play Pass the Pigs.
Is it like half the game?
No, it's a dice game, but you have pigs that you roll.
I have this
And
game.
depending on how they land, you get different
I
points.
have this game in a drawer in my house.
It's not Farkle, is it?
No, but it's fun. It's actual pigs. They're little pigs.
I have to
that
see
you
if I
roll.
can find it.
And you get like a point if it lands like on its snout, or a point if it lands on its feet.
I recall
or,
that I was bad at it.
Yeah, it's a lot of fun. So, a class of 52 students is playing Pass the Pigs. Use the results of the experiment to build a probability model for the way the pig lands. So, this is what they saw. The different ways the pig can land. It can land on its side with a dot showing or without a dot showing. These are the names for the different outcomes. I want a probability model, so I'm just going to add another column for the probability. So to find the probability, we need to divide each of these by the total. So we have to add them up first. So 3,939 rolls. So then to find each probability, you take the frequency divided by the total. So the side with no dot. I take 1344 divided by 3939. Just so you guys, all I'm doing is dividing by the total. So the next one I do 1,294 divided by the total. Does everyone understand how we got those numbers? What should they add up to? 1. Is it possible that it won't be perfect?
Yeah.
Yes, because I did round to 4 decimals, but it should be very close. That's a nice way to just double check and make sure you didn't mistype one along the way, like I've been known to do.
Oh,
And I got 1 exactly, so
Put
it
it-
did work out.
put a negative instead of a decimal
Oh.
when I was incredibly.
That would make a difference. So there's my probability model. Each outcome with its probability. So what's the probability that a pig lands on a side with a dot? So if you have the table, all you have to do is go read it. Side with a dot is,
0.3285.
if you say 32.85%, that is also okay. I don't care which way you answer it. Would it be unusual to throw a leaning jowler? What's the probability of a leaning jowler?
0.0081, way less than 5%.
That's a 0.81%. So is that unusual?
Yes.
Yes. Anything less than 5%.
How do you even, what is that? What is a leading shower?
It has to be like on its snout with one leg.
Wow.
It's a fun game. You should play it sometime.
Sure.
Highly recommend it.
Yeah, can we do that for final week once we're done with our final?
Yes.
Or not even done. That's for our final.
Or
That's
your
our final.
final.
Our final is.
Okay, the winner gets an A.
Everyone
Second place
else.
gets a B.
No,
third
not
place-
that. We do this, but with that.
We do it until we all
Oh,
throw a
oh.
leading jowler and we record. Well, we record our frequency and then we see if they line up. Go back to this example.
With Z-scores and everything. Yeah.
So this is all based off the empirical approach. It's basically what we saw. Okay, we looked at when we rolled our pig, this is what we saw, this is the probability based off that. Classical is basically saying how many outcomes are possible, how many of them are the ones I want. Okay, it's essentially very similar, but it's not based off what actually occurred, it's based off what could occur. So if I look at this, we have a fun-sized bag of M&Ms containing 9 brown, 6 yellow, 7 red, 4 orange, 2 blue, 2 green. Okay, suppose a candy is randomly selected. So this isn't what did happen when I selected, it's what could happen. Okay, that's the only difference. In terms of calculating our probability, it's the same, part over the whole. What's the probability that it's yellow? So how many yellow candies are there? 6. Out of how many are in my bag? So you have to add them all. So 6 out of 30 is 2.2. What is the probability that it is blue? So how many blue candies? 2 out of 30.
0.067. Except for I said that wrong.
Yeah, you said
that
last year.
I meant to say 0.0 in my brain.
Okay, so what's the difference between blue and yellow? Which is more likely?
Yellow?
Yellow is more likely. Which shouldn't come as a shock because there are more yellows in the bag. I know, it's crazy. All right, let's do just a couple more looking at this. And then I'm going to give you guys a chance to practice. So Sophia has 3 tickets to a concert, but Yolanda, Michael, Kevin, and Marissa all went to go with her. To be fair, Sophia randomly selects 2 people who can go with her. Determine the sample space. So I am selecting, I have 2 slots, right? So the sample space is every possible outcome with these 2 people. So I have 4 that I'm choosing from. Can I abbreviate these names?
No, write them out.
So Yolanda is going to be Y, Michael I'm going to say M-I, Kevin is K, Marissa I'm going to say M-A. So if I select 2 people, my 2 people could be Yolanda and Michael. Or it could be Yolanda and Kevin. Or it could be Yolanda and Marissa. Okay, that's every option with Yolanda. What else could I have?
Mike and Kevin.
Michael and Kevin, or
Michael and Marissa.
Marissa or
Kevin and Marissa.
Kevin and Marissa. Does order matter in this case? No. Just selecting two people. So how many different options are there?
6.
Alright, 6 different ways I could select 2 friends. So the probability of Michael and Kevin, there are 6 total. How many of them are Michael and Kevin?
1.
So it's a 1/6 chance that Michael and Kevin get to go together. Okay, the probability of Marissa. How many of these have Marissa in them?
3.
3. Out of,
6.
so 0.5. You can give me a fraction. If you do a fraction, I want lowest terms or decimal. So either fraction or decimal, but in a fraction needs to be lowest terms. So if I ask you to interpret the probability here, what does that mean?
Marissa's.
It's like a percent. So there is a 50% chance of what?
Marissa.
So there is a 50% chance that Marissa gets selected. Any questions there? Two more slides. A survey asked 500 families with 3 children the gender of their children. It was found that 180 families had 2 boys and 1 girl. So estimate the probability of having 2 boys and 1 girl using the empirical method. Empirical is what happened. So for my empirical method, how many total families did I have?
5.
How many of them were 2 boys and 1 girl?
1 and 3.6.
This example is just kind of showing us the difference between the 2 ways we can calculate probability. Empirical is based off what we saw. Classical is based off what could happen. So if I were doing the classical approach, I would have to list every possible combination. So of my 3-child family. So boy, boy, girl, or boy, girl, boy, or girl, boy, boy. And we have to list all these. That can get a little confusing. If that is a problem for you, you know, when we just had 2 children, it wasn't so hard. The 3rd child makes it a little harder. We can sometimes draw a diagram that might help too. So if your first child could be either a boy or a girl, right?
Oh.
That represents the first child. Then the second child can be a boy or girl. So from each of these outcomes, we branch off. So if we look at our 2-child family, we could have boy, 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 girl, girl, boy, girl, girl. Is this every combination we listed first in that first example? We have a 3rd child. So from each of these outcomes, we have to list the next outcome. So from each of these, it could now be
Boy and girl.
boy or girl. This is what's called a tree diagram. Certainly not required, but it can help you if you're struggling to list all the combinations. So I want to know how many are 2 boys and 1 girl. First, how many total outcomes do we have? There's 1, 2, 3, 4, 5, 6, 7, 8. Would you guys agree there's 8 different ways we could get to our 3-child family?
Yes.
So, 2 boys and 1 girl. So it could be I went boy, boy, girl. Or I could go boy, girl, boy. Or girl, boy, boy. Is there any other outcome that has 2 boys and 1 girl?
No.
So it's 3 out of 8. If you wanted that in decimal form, you could certainly divide them. Fraction is fine, but it is 0.375. So you can see classical is what everything that could happen. Empirical is what did happen.
I mean, that's pretty spot on.
Yeah, we weren't too far
far off.
Is that okay with everyone? Final thing, there is something called subjective probability, but it's hard to give you many examples over that. Did I not have that definition on there anywhere?
Yes, it's on the Twitter.
I did, I just broke them up. Subjective is based on personal judgment, so that's like the weather. You know, if they say there's a 75% chance of rain today. It's not totally a guess, it's just based off what they have seen. And two different people might come up with two different probabilities. If I were saying, you know, based off my past students, I would say there's an 80% chance you'll get an A on the next test. Okay, is that, like, do I have hard facts that I'm basing that off of? No, I'm using my personal experience. So subjective is kind of a little sketchy. You don't know for sure. We can't just sit down and calculate that. All right. The homework. I am going to give you book problems, but please listen carefully. A lot of the questions will say find and interpret the probability. If it says find and interpret, you don't have to do the interpret part. Okay, just find the probability. The only ones I want you to interpret, I think there is one question where it's the only thing that the question asks. Like part A says find probability, part B says interpret it. So that's the only time you have to if it's the only thing the question asks. Otherwise, all of these that say find and interpret, just find the probability.
Like if it's part A and B, please find it.
Yes. So that is your assignment.